Hello everyone. We are Group 21 and our project is heartbeat abnormality detection using audio feature engineering. And our goal is to detect the abnormal heart sounds using PCG audio recordings. And PCG stands for phonocardiogram, which is simply a recording of the heart using a digital stethoscope. In a normal heartbeat, we hear two sounds, S1 and S2. These represents valve events in the heart. When abnormalities occur, the timing, energy, or the spectral characteristics of these sounds shift. That's why PCG signals can reveal conditions like murmurs or valve dysfunction. We are using the um, Physionet 2016 heart sound dataset, which contains over which contains over 3,000 recordings. Each recording has an associated .he file that labels it as normal or abnormal. Here in our report, we can see the dataset details like a sampling rate, number of features, and the distribution of classes. Yeah, this is the pipeline of our project, and the heart of our project is building an end to end pipeline that goes from raw PCG audio to the machine learning predictions. Our pipeline includes loading the dataset, preprocessing the audio, detecting S1 and S2 peaks, extracting the engineered features, applying normalization and PCA, training uh, machine learning models. From that, we visualize the ROC curve for the prediction, whether the model is working good or not. Now, my teammate will walk through the implementation, starting with how the process of raw audio.
Um, Here we start by loading all WAV files in the dataset and reading their HEA metadata files. The HEA files contain text that includes the words normal or abnormal. So our first task was to accurately extract labels for every recording. Uh, Here in the code, you can see our label extraction logic. We assign a label only if the HEA file clearly states normal or abnormal, and we skip anything marked unknown. So next, we pre-process every PCG signal. We apply a 20 to 400 Hz bandpass filter, which removes baseline noise and high frequency artifacts. We then normalize the amplitude of the signal so that everything is scaled consistently. After filtering, we compute the Hilbert envelope. Here's an example for our output. The top plot shows the original noisy heartbeat signal. The second shows the filtered and normalized signal. And the third plot shows the envelope, which makes S1 and S2 peaks easier to detect. Uh, to locate S1 and S2 events, we smooth the envelope using a moving window and detect peaks using adaptive thresholds. We also apply psychological timing rules. For example, systole typically lasts between 0.15 and 0.45 seconds. Using these rules, we classify the peaks into S1 and S2. On this plot, um, you can see S1 labeled in red and S2 in green. The segmentation is accurate enough to extract features from each cardiac cycle. Now my friend will continue.
So, coming to future extraction code, so that table of first few future rows coming to once S1 and S2 peaks are identified, we extract a rich set of engineered features. For each cycle, we compute duration of S1 and S2, RMS energy of each, and spectacular centroid and spectacular entropy, systole and diastole intervals, systole to diastole ratio. These features capture timing, strength, and spectacular shape. So, coming to surrogate breathing place heart energy plots. We also include cross signal correlation features, which compares the low frequency modulation of the envelope representing breathing with heartbeat energy. These features capture synchrony between respiration and heartbeat behavior. Now, coming to wavelet packet future code, which means like WPD output. To capture murmur like patterns and multi scale frequency characteristics, we apply wavelet packet decomposition. We compute the energy and entropy of each frequency band and derive a high frequency to low frequency ratio. So, next coming to PCA plots. After assembling all features, we standardize them with Z-score normalization and apply PCA. The first 10 principal computes capture most of the variance and reveal clear separation between normal and abnormal patterns, as you can see here. So now my friend will continue.
Uh, so, coming to the confusion matrices with our final feature set, we train three machine learning models: logistic regression, random forest, and support vector machine. Uh, So this is the correlation heat map that we got. Uh, so uh, uh, Comparing all the three machine learning models, the random forest performs best overall. Here is we can see the clear separation between the normal and the abnormal classes in the confusion matrix here, and in the ROC curves also the random forest gives the highest AUC, indicating uh, the strong classifier reliability. And so to conclude our uh, yeah Yeah. To conclude, our project demonstrates that engineered acoustic and psychological features can effectively distinguish normal from abnormal hard sounds. Our full pipeline, processing, segmenting, feature engineering, PCA, and machine learning, achieves strong performance on the PhysioNet dataset. Uh, Finally, from the project, uh, we identified the unlabeled data set, whether the heart signal is normal or abnormal. We got them, uh, we printed them in a CSV file as a result. That's the prediction that we got at the last. Thank you for listening.